Thanks everyone for coming. Thanks Sarah for the introduction. So my name is Jamon Van Den Hoek. I have a presentation today on remote sensing principles and applications. I think you're familiar with some of these ideas, and I think a lot of this is going to be new, but I hope this resonates with you, and please ask questions as we go or at the end. Yesterday at ESA we saw the latest and greatest. I'd like to take a step back just to talk about sort of how far we've come really with space-based remote sensing. This is the first image ever taken of the Earth from the upper atmosphere of the Earth, of space and the Earth's atmosphere. This is from 1946 with the V2 rocket. As you've seen, we see rapid development in our remote sensing capabilities over the subsequent decades. In 1929, we have the first satellite view of the Earth, and it's a very blurry, sort of askew snapshot. We have the television, the first television image, in 1960, the Tiros-1 satellite. And then as we put people into space, in 1968, we have a full color image taken by the Apollo astronauts. And this view from space was, of the Earth from space was revolutionary. It of course, was completely unprecedented. There were imaginings of what the lunar surface looked like, what the Earth looked like, but no one had ever seen this before. And at first, the value was, wow, like look at the pale blue dot, right, against the backdrop of space. But in remote sensing, we go far beyond that. Rather than appreciating, but still sort of viewing the Earth from a distance, we are actively measuring or actively assessing change. And in some cases, we've been doing it with a system that's been consistently collecting about the same kind of data for over 30 years, and that's the Landsat system. This is a snapshot of the NASA Earth observing fleet, almost complete as of last year. You'll see some of these systems that I'm sure you're familiar with, Landsat 7, Landsat 8. We also have some precipitation systems, TRIM, atmospheric carbon dioxide, Terra and Aqua, both house the MODIS sensor. A bunch of other systems. These form quite a robust monitoring fleet that allow us not every minute, but certainly every day, every week, every month, some refresh of the global condition. And in the talk today, I'll be discussing how we make use of all these data. I think it's a worthwhile sort of conceptualization to think of us as being on the Earth as living inside of this machine, kind of like a gyroscope that's orbiting around us at all times, constantly collecting streams of data on the Earth's surface, not so much on us directly as individuals, but on how we affect the Earth's surface and how we affect the atmosphere, the waters, and the frozen regions. There was a question yesterday that's a little bit difficult with the contrast of just about space junk and the number of satellites. This is exaggerated, but you can see space is crowded. There's a lot of space junk out there. There are approximately 2,300 operational satellites in space right now. That's communication as well as Earth observing and just relaying satellites. So it's dense, it's sort of a delicate ballet to coordinate all these movements, and that's regulated at an international level. So this is Landsat 8. This is the most recent NASA satellite, in a sense a colleague of the Sentinel-2 platform that we learned about yesterday. It works a little bit differently than Sentinel, but both of them give very comparable kinds of data as we talked about. This is an artist representation where Landsat's sort of like viewing from heaven or something. I don't fully know, but it's very like glorious, and it's probably the best image I've seen, because satellites look really weird. They are not elegant looking machines. They're very like brutally pragmatic, and this actually makes it look nice with like rainbow colors and everything. So remote sensing gives us these an image like this. This is just a screenshot from Google Maps. satellite background. This is actually aerial photography. But this is the world, right? This is a landscape. We have agriculture, we have roads, we have a settlement in the middle. This is raw data. This is just an image that you could take out of a plane flying over. What we use remote sensing to do is identify the key indicators on the ground, and we try to simplify those. So this is though we can interpret this well, because we've seen landscapes like this. We've probably seen hundreds or thousands of these in our lifetime. We're interested in parts of that landscape. We don't want everything, we want to simplify things, right? A bunch of information, potential out there that we want to compress into data, and we want to make decisions with those data. So we identify variables, or we could think of spectral characteristics of the landscape that are associated with some process of interest. Sarah and Laura were just talking about conflict, talking about drought, talking about displacement. That would be a process, right? And then with remote sensing, you won't see people being displaced, but you'll see the consequences of that displacement. So we look on the landscape to see the consequence that's related to that process. So it's a lot of indirect observation. And we try to abstract and simplify, and this is all cartography really is, right? We're trying to make clean maps. We're trying to make good visual representations of what we see on the ground to clean up this representation. So if I was interested in locations of street intersections, this is a much, much easier image to work with than this, right? Plain to see that. Same idea with remote sensing in general. We're not going necessarily to a cartographic product, but we're trying to improve our visualization. We have a variety of sensors to do this, obviously. Notice, which has been in operation since 2000. This is a coarse resolution sensor, so 250 meter, 500 meter, and 1 kilometer pixel cell size. Nice thing about MODIS is, we'll talk more about this, but it takes very broad images, so we call that the swath width. But a single image from MODIS covers extreme distance. Landsat, nominally 30 meter resolution. We currently have Landsat 8 and 7 in operation. We lost Landsat 5 a couple of years ago after being in service for about 30 years. We all know about Landsat, finer spatial resolution, high number of bands. And then we have a whole sort of scattershot approach with very high resolution, primarily commercial remote sensing systems that give us much more detail spatially, a little bit more limited spectrally than what we traditionally would see with Landsat, MODIS, or the Sentinel constellation. But these all are brought together in the work that BAM does. These all get brought together in trying to characterize the kinds of changes that we can see on the ground and assessing the condition at different scales. We may be looking at landscape level processes, 50 kilometer by 50 kilometer, or we may be looking at very focused, say, small scale subsistence ag. We have a variety of sensors that allow us to move across resolution and extent. And these sensors also, this came up at ESA yesterday, they allow us to get different snapshots at different times, different seasons, not so much the time of day, that's basically fixed to about 11 a.m., but different seasons and over many, many years, right? So we have this take on seasonality, cloud effects, phenology, natural green up, all of these things can be captured with remote sensing and characterized, and these are the real critical relationships. How do we balance temporal frequency with spatial resolution, and how do both of those influence just what we can do with those data? Some of the things that would tell us about what we can do or should do just depends on our application. So we have here on the x-axis nominal spatial resolution, so that's basically how big is your pixel. And then we have the resolution, temporal resolution on the y-axis in years. So if we want to look at 1 year, just an image, one image per year, well that's suitable for some kinds of land cover if we just want to do inventory to assess where there's agriculture, to assess where there's forest. The global forest cover maps are not done every week or every month, they're done yearly, though of course there's value for some early warning systems that look at much more rapid intervals. If we're interested in geologic formations, we don't need that daily. Maybe that's every 100 years, right? Geology just doesn't change all that much. Topography as well, there are obviously landslides, there are changes, there are earthquakes, but it moves at a much slower pace, so we can use coarser temporal resolution. Going towards the direction that VAM tends to work in, emergency response, well, you need the data yesterday, right? And then you need it again today, and then again tomorrow, and maybe twice today. So that has very high temporal revisit needs. Precision agriculture is sort of a similar area where we're looking at subtle changes week to week to week. And as we shift to coarse spatial resolution, if we want to understand, say, the path of a hurricane approaching the southeast United States, we do not need to know the hurricane at a 1 meter resolution. Much better to look at it, say, 1 kilometer or 10 kilometer, right? That would be complete overkill to be characterizing, say, Lake Victoria with 1 meter data. There's no information, that's just too much information at 1 meter. It's much more effective to say, look at 50 meter, 100 meter, maybe even a kilometer. So these are the balances that we think about when we choose a kind of data set. And a lot of it, of course, is just what has worked in the past, right? But that was informed by this kind of decision making. Now, in that last slide, I use this term land use and land cover. They're often used interchangeably, but a helpful distinction, and quite a formal one, is that land cover, which is what we're looking at here, refers to biophysical and ecological characteristics of the Earth's surface. The land use was the use of that land cover, socioeconomic use, right? You could have a forest, but that's used as a plantation. So the land use would be a plantation, but the land cover would be forest, right? Croplands sort of blur that boundary because you would have commercially raised corn, well, but the crop is corn, so they're effectively equivalent. Wetlands, land use may be tourism, but the land cover is wetland. So some terminology that's helpful, I think, going forward, just to avoid some of the confusion. And this is just one example of many now global land cover products. There are probably a dozen competing land cover products at various spatial resolutions made at different times, starting from 2000 to the present. So this product that we were just looking at came from remote sensing. Came from MODIS and another system called AVHRR, which predated MODIS. Remote sensing is more than just spatial resolution and more than just bands. We have an orbital component, right? Of course, we have the spatial component, which we're probably most familiar with, the resolution and the extent. We have a spectral component, which is what kinds of electromagnetic energy, what kind of light are we measuring being reflected off of the Earth's surface, or in the case of clouds, off of the atmosphere. The spectral component, the design of what we would call bands in multispectral imagery allows us to differentiate between different kinds of energy. So we'll talk more about this, but we look at red light separate from blue light, separate from green light, separate from near infrared light, because there's different information in each of those bands, and we want to discriminate features based on that difference. There's a temporal component, which we talked about, so that would be the time of day, which we tend not to have much control over with satellites, and then the revisit period, so how often does it return. There's also a radiometric component, which we won't be talking about here. This doesn't really affect remote sensing data users all that much. Really what it comes down to is how narrow a difference, how subtle a difference in energy can you detect. So if you have a very, very subtle difference between one wavelength and another in terms of the amount of light, you need a very fine, a high radiometric resolution to detect that difference. And we won't really be messing with that all that much. That's sort of baked into the system. These components together basically allow us to detect features or assess condition, assess change in the presence or absence of features or change in that condition. So let's start with the orbital component. This is a really simple schematic. showing a pretty standard orbital system. This is one that's used by many satellites. About 700 kilometer altitude. We have some inclination, so it's angled a little bit off of the North Pole, so it's not just going North Pole to South Pole to North Pole to South Pole. Does anyone know why we don't just go North Pole to South Pole to North Pole to South Pole? What's the advantage in not doing that? But if we did that, we'd be hitting the North Pole every single orbit. And if we put it off the axis, we are covering other parts around the North Pole every single orbit, right? Gives us a little bit more coverage. It's obviously a design that is not focused on polar observation. If you had specific interest in polar observation, you would not be so far off the poles. As I mentioned, this time of day doesn't really change. It can go from 9 a.m. to 10:30 a.m. That's built into the orbit. That's it. And then we take this track and we project it onto your surface, and that's where our collection of data happens. And then however long this orbit is, if it's a day, if it's every 5 days, if it's 16 days, we just build up image acquisition over time. For Landsat, this is how that looks. We collect the first orbit here, then we shift, collect the second orbit, shift to third, fourth, and you can see we just do this loop until we come back, basically register. On the 16th day, then we're taking redundant data sets, or observations. So I'm not going to talk too much more about orbit, but orbit really sets the stage for spatial. So what part of the orbit do you think, on this slide, influences our spatial resolution that we would have? Altitude, right? Main one. The farther away you are, the bigger the pixels you have. What else might influence spatial characteristics like spatial resolution and swap width? How wide we can look at?
Equipment.
Say it
The
again.
camera. Equipment.
So what about the equipment specifically? Everything else happens at the equipment. Yeah.
I know, the better sensor, the better camera is.
One thing that's related to that is just how narrow of a view do you have, right? So if I had a flashlight here and I turned it on and put it at the wall, the beam of the flashlight's going to spread. It's the same thing with the sensor, right? So if you have a really narrow beam, you get a very small spatial resolution, and well, should have a small spatial resolution and a small swap width. You're just not covering as much area. That's called the instantaneous field of view. This again is built into the sensor. We also have just what angle are we looking at? Are we looking at the Earth from an angle or not? And where are we on the Earth? Because the Earth does have a curvature that is not consistent, so that affects it as well. But it's really, these two are the main ones, right? And so you can already see that we're a bit indebted when we talk about spatial characteristics to orbital characteristics, and we'll see as we go forward that spatial influences spectral as well. And both of those influence temporal. So we can't really get away from spectral, spatial, temporal. They're all really bundled up. When we talk about spatial, most people think about these high-res systems. Earliest commercial system, Iconos. Does anyone know of an earlier system to Iconos that had sub-meter resolution?
KVR.
What's that?
KVR.
What's
The
KVR?
Russian stuff.
Is it a spy satellite? Yes. The answer is spy satellites, right? So I didn't know about KVR, but there's an American system called Keyhole, which is like you're looking from space through a keyhole. That was operating in the 60s and 70s with less than 1 meter, half meter resolution. But it's a totally different game now with high resolution commercial imagery. We take many more images on demand, globally, daily. Like that, this is an unprecedented, as the ESA representative was talking about yesterday, this data collect is really unprecedented. There are challenges though. If we want to take a scan of, say, let's try to assess subsistence ag across sub-Saharan Africa, wall to wall, and we have this red bounding box. These are really small strips of data that are collected by high-resolution commercial imagery. They're very they're tiny really compared to others. And they're tiny because of the orbital characteristics and the spatial resolution and just the data volume. You have such high resolution, you can't take a single image that covers half of the breadth of Africa because that's just going to be, I don't know, petabytes. It's going to be huge. So you have to split it up. And it gets split up in this sort of grid-like long strip approach. This is really different than other systems. This is the MODIS swath with just across the Midwest in the United States, the Great Lakes area. We get the entire Great Lakes region, and in fact, we only need 3 images to cover the breadth of Africa. So it's a completely different system, completely different data management approaches. In no way is MODIS better, in no way is high-res better. It's totally dependent on the application. Landsat then, sort of falling in the middle, operates, well, in the middle. We have many, many observations that require us to cover the continental breadth. But we would choose Landsat or MODIS or higher for the specific application. And data volume could be part of that discussion. So when we think about scale, we should talk about a couple of different definitions of what we mean by scale. Does anyone have an idea of what this is in the top image? What are we looking at in the top image? It's a radar image. What else?
The LP carries.
It's an LP, it's a phonograph, you guys got it. So it's a groove in a record, right? At this scale, though, that we've zoomed in at such fine detail, I'm not saying it looks the same, but you see some similarities, right, in sort of geophysical, this canyon view. In fact, this is incredibly small, 20 micrometers. A micro is 1/1,000,000th of a meter. Really, really small detail, and we start seeing some similarities. Maybe that's a canyon, right? Kind of does look like radar with that image. This is one way of thinking about scale. It's a way of characterizing the kind of phenomenon at a specific spatial unit. That's the same kind of thing that we think about with remote sensing. What's our scale of observation? What's our spatial resolution of observation? We could have high resolution imagery here at ½ meter, going all the way up to 80 meter, and we lose clarity of the image, right? We've lost the detail. These 2 houses here end up sort of getting merged into these lighter gray pixels, but we've lost a lot of clarity that we see with high resolution images. Let's go from the other end. This is an image from Landsat. This is a false color image, right? We've got the red. Anyone have an idea what this is? Totally out of context. Vegetation, right? We know there's some vegetation. What might these dark pixels be? Water. We got, well, we're already halfway there. Water and vegetation, a little bit better. This will be a Sentinel-2 false color composite. You can see there's really a world of improvement, spatial resolution-wise, when we transition to Sentinel-2. Still water and vegetation. 4 meter, we start seeing a little bit more clarity. There's a path. We see some coastal turbidity. Individual tree crowns, that's what it looks like they're coming out. 1 meter resolution is quite plain, right? We have football pitch, tennis courts, parking lots. These look like cars. You can even see a bridge linking. It's a little island. We zoom in, same resolution as last time. We can go further and further. Now, 0.2 resolution is not currently possible with satellite, commercial satellite image acquisition. Of course, spy satellites get this. Drone imagery, aerial photography. At this resolution, we're capturing amazing detail. We can basically tease out a whole host of features that would be lost even at 1 meter resolution, like individual cars that sort of get muddled together. And this is the trade-off, right? 30 meter resolution. Let's put a house in a 30 meter resolution block. That blue house against a red background, that makes the pixel look blue. It's not going to be as blue as this, but it basically drowns out this pixel, so it ends up looking very, very blue. If we go to a finer detail, 5 meter resolution, Now we're able to capture some of the features that make up the house's footprint. These 9 cells in the upper left-hand corner are still dominated by red, and so they're going to stay red. Now, this is a very simple, whatever covers the pixel the most, the pixel is colored that way. It doesn't quite work that way, but similarly, at 1 meter, we're doing a pretty good job at capturing the house, right? So these sorts of trade-offs are critical for trying to detect small-scale plots, individual settlements, roads, things that we are basically just going to get lost. The background, typically, in 30 meter or even 5 meter, we may need to go to 1 meter or even half meter resolution. Another way of thinking about that, at a very small resolution, very, very high detail, we can capture individual rows. And when I say that, yes, we can look at the pixel and see that that is a row crop, but we can also measure things like Ndvi off of it. Now, if we switch to this intermediate ground resolution size, same area generally, but we've got much coarser pixel size. And to my eye, we've got 4 different rows, and then we have 3 different patches where there is no crop. How do you think the Ndvi, let's say this is a high Ndvi here, how do you think the Ndvi will look in that intermediate pixel? Just as high, very, very low, somewhere in the middle?
Somewhere in the middle.
Somewhere in the middle. Why do we have somewhere in the middle?
Because it's a mix of.
It's a mix, right? It's a mixed pixel. This is a main challenge in remote sensing, is knowing that what we see in the pixel can be directly attributed to a feature. Otherwise, we have this mixed pixel scenario, which of course, as we just get more and more coarse resolution, it just becomes more aggravated. There we have 2 different types of crops mixing together. So we can still measure Ndvi here, but this isn't Ndvi of the row crop, right? This is Ndvi of the row crop plus the soil in between. And if we tried to make a map where row crops were based on this, probably not going to do a great job, because you're getting this big mixture of signals, and you can't discriminate the crop from the soil. So you, in this case, you may need this detailed image. Even then, though, the pixel could cover half the soil and half the crop, right? So these are considerations that have to be brought in when we think about what are we actually seeing in the cell size. And this varies across different landscapes. For agriculture, so we have field photos on the left-hand column, then high resolution in the second and third, and then Landsat on the right-hand side. Agriculture, if it's small-scale agriculture, we really may need this high resolution. Evergreen forest, we could be totally fine with Landsat. In fact, the global forest cover products right now are derived on Landsat data, and in many areas they're very accurate, in other areas they have challenges because of things like mixed pixels. Mixed forests, well, different kinds of vegetation mixing together, difficult to do, to discriminate individual types with too coarse of data. Residential data, it's just a huge blur with Landsat. We defer to the high resolution here. Shrubland and water, depends on the extent. We also have a global water map right now that was developed by JRC scientists that uses Landsat 30-meter data. So despite the obvious advantages for a lot of data sets, for high-resolution data sets for detecting different kinds of conditions, all of the calibrated global products dealing with land cover, forest cover, or water are all based on 30-meter data right now. There are some new products that are coming along. They're using Sentinel, but those are only a few years old. The others give us, say, a 30-year record. So let's transition to spectral characteristics. Main message with spectral characteristics of an image is we have visible light here between blue, green, and red. We have ultraviolet, which would have shorter wavelengths, and then we go into the near-infrared and then mid-infrared, and eventually radar waves with much longer wavelengths. But our sensitivity, our eye sensitivity, is in this visible range, right? Blue, green, red light. Nominally about 0.4 to 0.7 micrometers. And just like our eyes, satellite sensors work by detecting, by measuring these different kinds of light and being able to say that something that has a peak, so something that increases and has the most light reflected off of it, that's all we can detect is things that bounce off. When that's in blue, well, we just call that a blue feature, right? When it's in red, we call that a red feature. And our eyes can detect trillions of variations of colors. Satellites, not so good, but I find it really fascinating that our eyes actually, where we're most sensitive to light is like right here. So our eyes are designed to capture this visible light, and we have this amazing sensitivity right in the middle, in this green band. So we've evolved to be very, very sensitive to specific wavelengths and less so to others. Satellites work the same way. We want to be able to discriminate blue from green from red features, and more to the point, be able to identify what a feature may be because it looks this much blue or this much red, right? We want to be able to assess this condition. Similar kind of representation here, blue, green, red. Has anyone seen a plot like this? This is a specific kind of plot.
Deep space, stars.
It's related to stars. Yep. Bunch of gaps here that are related to specific kinds of things that happen with stars. What would the gaps represent? The black spaces in between the sort of green light section. What does that represent?
It's different elements that come out of the stars, right?
Very close. So we have, this is a signature of the light that comes off of the sun. And because of the sun's molecular components, some of the molecules in the sun, so the sun generates, virtually all of our light as it comes down to Earth, and then reflects off and goes back into space, and we measure that with satellites. Some of that light on specific wavelengths never reach us because the sun itself absorbs that light before it leaves the sun. So we don't just have a complete 100% light emission from the sun in every wavelength, invisible light. We have gaps. And that's the light that basically the sun doesn't want to let go of. And at the top we see that there are many, many more gaps with blue compared to green, and especially compared to red. Why do we have so many more gaps in blue? And this might help give you an answer. Why is there so many more missing wavelengths of light in blue compared to red?
The shorter wavelength.
Shorter wavelength, so smaller, and just more likely to hit something that is bigger than it, that's going to absorb it, right? This is the same reason this is called Raleigh Scattering, effectively the same reason why our sky is blue. Blue wavelength light reflects and refracts much more actively than other kinds of light. Also, it just gets more absorbed, more commonly absorbed. So we have a transition here. What this means is that this wavelength of light, I don't know exactly what it is. We'll never see this with our eye naturally. It never comes to us. Neither will we see this with the world. So the sun grabs it, but in reality, the vast majority of light the sun emits comes to the Earth. Now, once it comes from the Earth's surface, or the Earth's atmosphere rather, it hits our atmosphere, and there are many layers to our atmosphere which are composed of different molecules. Each of these are basically greenhouse gases as well as water. We have water vapor. These components in our atmosphere also absorb light. So there are these channels of transmittance where we can see light very well. So we see a lot of light coming through 3, 4, 5. Very, very little in 6 and 7 micrometers. So that's again a millionth of a meter, very, very small distance. This is all absorbed by water vapor. And not all, but virtually all. Much more transmittance again in the higher wavelengths and also in the very low. This is where we see. It's our visible
No,
It's
we see on the left.
235. Sorry, 345.
Micrometers? Are we in?
548.
We're seeing here.
Yes, this is 0.4 to 0.7.
Yeah, this is the visible light region here.
No, it's on the left. This one.
These are different.
Micrometers and
Am I going across scales?
Zero
Oh, thanks.
points.
I'm clicking across different scales. Thanks. Right, micrometers, not nanometers. So we see these massive areas of absorption. These are of transmittance. These are areas where we have good likelihood of getting reflected light. So this is where we basically want to operate if we don't want to be interfered by the atmosphere. So sun transmits light, comes through the atmosphere, bounces off different features on the Earth's surface. We call that the incident energy. When we say energy, we really mean light. Most of that, in most features, is going to be reflected. In some cases, it's going to be absorbed or it's going to be transmitted. We only work with this reflected energy. If we look at an image of nighttime lights, that's an exception. That's transmitted energy. That's us generating the light and that going off into space. But for Sentinel-2, for Landsat, those work with reflected energy. So totally dependent on how things reflect. And thankfully for us, different things reflect differently, right? Here we have 3 different curves. We're looking similarly across these wavelengths. Dry, bare soil, vegetation, and water. Water's down here. Vegetation is the solid line, and then dry, bare soil is this kind of line that arcs, goes to the top. To our eye, we know that vegetation, soil, and water look very different. When we do that, we're really just looking down here, right, in the visible wavelengths. Beyond that, though, into the infrared, there's a ton of variability as well, and in fact, much more variability. Here, this is a pretty narrow range, 0 to say maybe no more than 30%, I would say. So this is our little range here that we're working with, and of course, dry, bare soil reflects more than vegetation, and water reflects the least. Okay. But if we go beyond that into near infrared and then short infrared, we see these huge gaps, these huge separations. And water especially virtually absorbs or transmits all of this energy in these wavelengths. So water looks completely different in these different wavelengths. And vegetation and soil, especially in a wavelength like this, have a much bigger difference, right? And so we want to design a system that looks maybe here. If we want to design a system that's perfectly built to differentiate soil and vegetation, maybe we would have we look in this area, and then we look in this area, and maybe here, right? Those are the 3 areas where we see the biggest difference. If we're going to look anywhere to see difference, that's where it is, those 3 wavelengths. So when we think about all other kinds of features, there's a lot here. It's kind of a messy chart, but these are more infrastructure or sort of settlement related. Grass, slate, concrete, brick, asphalt, astroturf. Very, very different characteristics. Look what's happening at astroturf, right? Like fake grass used in sports arenas. We have this peak in green, except it looks like fake grass. But then after that, very little else. It's been designed really just to look green, look like grass only when you look in this one part of the spectrum. And then after that, it has a very kind of as far as I would understand it, a non-engineered design, right? So it looks like this is the healthy grass curve, right? Sort of similar peaks in the same area, right? But then after that, grass shoots all the way up, and astroturf stays down. So if we want to distinguish astroturf from grass, not a good place to look, because they're designed to look very similar, but out here, they'll look very different, right? In the infrared regions. Even within just trees that can look, forest types that can look really similar in visible light, can look really different in infrared. And so we're talking a lot about vegetation here. This is why we tend to focus on near-infrared bands. Near-infrared goes into the calculation of Ndvi. That's why we look at near-infrared, is because there's so much separation. Not just vegetation to other things, but even within vegetation types. This changes over time as well. So this is a sweet gum leaves from 4 different times of year. Yellow, green, red, brown, different stages, right? Summer, fall, spring. They look very different. They look almost like completely different features. And we're really just, it's a function of missing chlorophyll, right? We have less chlorophyll, most chlorophyll here, less, and the least. So that green pigment gets lost, and we should be able to distinguish that. We'll look at some examples of that specifically. So when we choose when the satellite designers want to choose a specific location to set a band, to set a region of light they're going to be sensitive to, they're going to design it, they talk to the community, and they try to design bands that are sensitive to the features that they're interested in. So these are 3 example bands. Band 2, Band 3, Band 4, this happens to be from Landsat 7. These look very similar to Landsat 8 and Sentinel-2. These 3 bands allow good discrimination, certainly in the vegetation and other things in the, what's called band number 4 here, right? Good separation. Band 2 and 3, there's also some separation. These are the visible bands. Less separation in Band 2, pretty good in Band 3. Visible bands tend not to give us a whole lot, like analytically or quantitatively, but they're critical because that's what we see, right? We still want that true color image. So even though these don't have the most scientific value or value for assessing crop condition, these are still built into these systems just because we can interpret them so much easier. There was a question yesterday about how the bands from Sentinel-2 compared to Landsat. This is a graph showing that. We have in this row Landsat 7, in this row Landsat 8, and then Sentinel-2 A and B. Above that, you can see the design of Sentinel-2 for the visible and near-infrared. They worked in conjunction with the Landsat science team to ensure that Landsat and Sentinel could work together in sort of a continuity between missions. But Sentinel-2 went beyond what Landsat, any Landsat has done, and it added all these individual, much smaller, narrow range, so that means really sensitive bands, which are numbered 5, 6, 7, and those would fit right between red and infrared. And then we have, going beyond that, we have a mid-infrared band, band 11 and band 12. These bands are designed in such a way that we have some consistency, some complementarity. It means we can, to some extent, look at a Landsat 7 image from 2000 and compare it to a Sentinel-2 image that was taken today. It gives us some consistency. You actually have to apply a very, an algorithm to cross-calibrate and to harmonize the two so they can work together. But that's always been the design. So that's possible. So let's look at some of these false color images compared to natural color. This is a fall image, October 13th, red, green, blue. Look, similar area but different region, December 12th. False color using near-infrared red and green. This is the standard, what we would formerly call the false color composite, where we have 3 bands. It's called false color because near-infrared is being visualized with red. So where we see red here, of course, that's actually really means that there's high near-infrared reflectance. Red is then colored as green. So where we see green here is actually red on the ground. And then green is actually colored as blue. So where we see blue, if we were to look at that with our eye, that would look green to us, right? So there's sort of this shift in these bands. If we were to look at an image that we would call a panchromatic image, where we collect all visible light, it would just be a simple grayscale. looking at this sort of forest canopy. We look at that similar kind of grayscale, but sensitive to near infrared, we start seeing differentiation. We start seeing some tree types at this time of year showing much different condition compared to their neighbors. This is one of the tools that we use for looking at crop stress, for looking at insect stress, heat stress, drought stress. This, looking in infrared and other bands beyond the visible spectrum, allows us to basically isolate and identify areas that maybe have some sort of problematic condition. We're going to look at a American suburb, going to be like this. Cool water, bright blue, lots of healthy vegetation, roof types, some variation therein. So this would be like a drone or aerial image, allows you to distinguish. Now here's a good example where we have a lot of astroturf and we have natural turf. In this image, exact same, sorry, this is true color and they look pretty similar green. Here though, we see that that astroturf has very, very little reflectance in the infrared region, whereas the green grass and other healthy vegetation really pops out, right? So this is all built into the design of these systems. True color imagery, same idea, being able to separate between these. And then in senescence, at the time of year, to bring in a temporal consideration, when we'd expect these to look the most different, we certainly see much more variation on the landscape. So we have a choice of what time to look at the landscape to exploit this difference. The use of near infrared, does anyone know the history of near infrared? Any military buffs in the room? Near infrared came about in World War II. It was an American intelligence imperative to develop near infrared capabilities beyond what the Nazis and Axis had developed and were really sensitive to. And with some confidence that, in this case, the Japanese bomber planes were not measuring, were not taking imagery that were sensitive to near infrared. The American Air Force built a manufacturing plant just outside of Seattle in Washington State. And despite the sort of industrial background and like on the sea or on the coast, they made it look like a suburb, like a single, I don't know, maybe 2 or 3 block by 2 or 3 block suburb, and covered it in fake green grass. I know it's a black and white image. You can see how this didn't really work. This was meant to be camouflage, right? So they built all these houses, they put up all these fake trees, they even hired staff to deliver mail to make it look like it was a lived-in settlement. These houses look like a joke when we see this image on the ground, but from the sky, well, it looked like any other settlement. Well, what were they hiding? They were hiding B-2, or not B-2 bombers, but just fighter planes, a variety of planes that were being developed. This happened to be the 5,000th of these that was built. Difficult to see, but all the people that were working on this aircraft actually signed their names on this as sort of a commemorative, and then it got shot down over the Pacific a couple hours later. Not a successful run, but they built 5,000 of these, and they did it sort of hiding in plain view because fake grass looks like regular grass unless you look in near infrared. So that choice of looking in near infrared versus red, green, blue, when we say like blue, we don't mean, off to one side, we don't mean some wavelength in here. Really what we mean is a range of wavelengths that cut out blue light, a range of wavelengths that cut out green, and then red and near infrared and so on. Each of those bands then in a remote, in a satellite camera is going to be sensitive to a specific range of light. And in most cases, we collect many of these at the exact same time, or as close to the exact same time as we can. This is sort of a GIS view here, where we have multiple layers coming together. What this allows us to do then is to look at a given pixel and compare band to band to band to band. This builds up, in this case, 5 different attributes just for a given pixel. So now we're way beyond just talking about, well, let's look in green light, how do they differ? green light's one thing, but we can look at 5, we can look at, in the case of Sentinel, over 1,000 different bands, and each of those is going to have some information that allows us to compare and contrast features. So we've got this full spectrum here. Different ways to slice this up. If we look at 3 bands that were collected, same area at the same time, we have the false couple composite as usual. If you looked at those individually, they are grayscale. So you can look at an individual band and there's no color associated with it because it's just one value really. Grayscale, 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 but when you put them together, we color this one as red, this one is green, that one is blue. And that's how we get our false color composite. That's also why we can look at any given pixel and measure all the different values here. Now in machine learning and deep learning, which we'll be talking about more this week, we're not just going to go in and classify a feature or detect a feature or assess its condition based on band 4. You want to take as many, within reason, inputs into that classifier as possible and allow the algorithm to churn through and find the meaningful differences between all the different band inputs. And if you have good training data, you know that some combination of band 1 through 6, you know that that specifically looks like a lake. You know that another combination specifically looks like a forest canopy. So we developed a classifier to automate feature detection. In the Earth Engine workshop on Thursday and Friday, we'll be talking about working with all these multiple bands as well into a single classification approach. But before we get to any classification, these are working with different bands and doing visual interpretation with different false color composites beyond just the standard, red is healthy vegetation. Is really valuable. So there's an exploratory, sort of an interpretive stage that I think is important to make use of before you jump into some sort of automated algorithmic approach. This is a true color image, right? This is similar to what we see from looking at the airplane window. Standard false color composite, but there's myriad other composites. There's no best composite. There are standard ones that people have found that work well for, in this case, separating infrastructure from vegetation. Water still looks black because when you look into near infrared, or at infrared, we just lose a lot of reflectance from water. So water sort of gets lost in these, but golf course, so you can see the links really comes through. Infrastructure associated with roads and settlements really comes through. Different kind of take. This is just a subtly different 543 goes to 754. So we've lost band 3, we've added band 7, and we changed the colors. A different take on it. Again, exact same image, just we're looking at different subsets of that. And this may be the most helpful compared to this. So it's important to explore and sort of take stock of those. So let's talk about these 3 different kinds of sensors. One that we haven't really talked about, it's not used as much anymore, is a panchromatic sensor. This is just all visible light and maybe including some near-infrared light brought in. So these are grayscale values. These tend to have higher spatial resolution than the kinds of imagery that we looked at before because when you take a panchromatic image and you get all bands of light, you have much more light to differentiate a pixel. You have much higher signal than noise, and that allows you to have higher spatial resolution. So when you bring in more light, you're able to basically distinguish more features at a finer spatial detail. This is usually where we operate, a multispectral sensor, which is standard now. This is what we're looking at, 6 bands, you can have a dozen bands. There's also a hyperspectral sensor. Rather than carving out the electromagnetic spectrum into 1 for panchromatic or 4 for multispec, we can carve this out into hundreds and hundreds of bands. That tends to go beyond what we would typically use for food security. This is going to be looking at very, very subtle changes associated with precision agriculture, for example, or global scale sort of phenological changes. So doesn't tend to be used as much, and there are far fewer sensors that actually collect hyperspectral data as well. So with our multispectral sensor, this differentiation between bands is paramount value. Here we have an image showing red and near infrared. This is the same graph we looked at before, soil, vegetation, and water. This is where NDVI comes from, the Normalized Difference Vegetation Index. This started as VI, and that was just near infrared divided by red. That was one of the first vegetation metrics ever created. And then in 1972, there was this approach to normalizing that difference. So we take the difference divided by their sum, a near infrared minus red divided by near infrared plus red. And that gives us much more sensitivity. It also, because it's normalized, means we have a range of -1 to 1, which is a really nice standard range to work in. Healthy vegetation could be anywhere from 0.4 to really dense forest might be 0.8, 0.9. Water, usually below 0. Bare soil with no vegetative cover, very, very low. So these are typical values, and we see, same idea of setting up these bands, we want to exploit these differences. So the near infrared of the top one is vegetation there, really high near infrared, pretty low red. Vegetation doesn't usually look red, right? So it makes sense that we want to exploit that difference. There we get NDVI of 0.55. If we look at soil, different sort of range. So we go from 33 to 27, pretty low NDVI, and then water is 0 in near infrared, and then any value in red, it gives us a negative number. So that's what's happening behind the scenes with NDVI. There are dozens of other metrics out there. There are going to be some that are actually better for certain kinds of applications. NDVI is usually the place to start, but this was created in 1972. There have been a lot of advancements in 40 years. You may see an EVI, an Enhanced Vegetation Index. You may see NVR, Normalized Burn Ratio, which is actually designed for detecting burn forests. It's also very good for storage land. Lots of different metrics associated with infrastructure, water, and snow and ice. A lot out there. They all tend to work similarly like this, though. The math is usually pretty straightforward on them. We can look at some of the calculations in the Earth Engine workshop on Thursday. But NDVI is just a really good one to start with vegetation. So let's transition to temporal. This is a little bit dark here. Really similar example that we looked at that was shown in the ESA. This is a 10-year difference showing the typical fishbone pattern of deforestation. We have clearing of forest land with new road development, so it's a lot of change over 10 years, obviously. We see similar kinds of trends all over the world with globalization and urbanization. Here we have a 1972 image from the very first Landsat, and then a 2000 image from Landsat 7. This is Las Vegas. It is in a very dry part of the US in the Southwest, and it's really surprising, of course, to see all these golf courses that look really bright red, right? Really healthy vegetation in the middle of the desert. All irrigated land, pumped in from nearby rivers, and that has a lot of ecological consequences. So when we think about temporal, this is the quickest way to do it. Flickering back and forth between two dates, or just doing this side by side. But aligning that with the critical process at play brings a lot more value into it. So we know March 2011, the first shots were fired during the Syrian civil war. We can take stock of agriculture on that sort of nominal start of what is now become internationalized conflict 7 years in, to assess NDVI anomalies, so deviation during this month from previous Marches that we have on record. So it'd be 10 previous years of data. This isn't March compared to February compared to January. This is just looking at March, because with seasonality and phenology and land use, March year to year should look like March from other years, right? So we designed this system, we would design this interpretation to just look at March years, and we can do that throughout the course of the war. We see lots of improvement here. Green is above normal, right? So we see lots of improvement, still some below normal regions. And we can look in 2006 in the middle of the war, so we can do this 4-year difference. 2006 going back before the war, preceding, right sort of at the beginning or middle of the drought. And we can go farther back than that to 2001, which looks maybe the best of all these images. So by doing these comparisons, there's a number cut off there at the end, we can make year to year more confident assessments because we're looking at March every year. We're constraining our analysis. We'd expect some consistency in a given March image. And when we see deviation from that, and specifically in areas where we know that there's conflict or displacement, that's of course critical interest. Another example, here we have a farm, a false color image. No agriculture in this plot. Lots of shades of gray, so very, very little vegetation. Let's look a little bit later. And now we see vegetation. But the vegetation, the pattern is not consistent at all. So we've done this comparison. Obviously, one has been planted and cropped, and the other hasn't. But beyond that, we start seeing these similarities in the pattern, right? Apologies for these slightly different orientations. But you can see that these areas that in this image are brighter, higher tone, end up being less red in this image. And you see that throughout this plot. And what's happening in the background, it's other trends, right? This has been harvested, that's harvested. But in this plot, we see this sort of pattern coming through. Why do we think that there's a difference in condition here, right? If we assume it's the same seed, same quality of seed, it's really close, right? So it's not climate differences or anything. But what do we think is happening here? Soil, right? And what's happening in the soil?
Moisture.
Different moisture, right? So if we go here, darker areas would be more or less moisture? More moisture, right? Higher areas kind of get parched and dried out. So really what we're looking at, certainly soil, but it's these subtle differences in where the soil, the water profile is. You can actually see a body of water here on this landscape, and that directly correlates to the condition that we assess here. Where we had higher conditions, higher elevation, or perhaps a different kind of soil that had less water, we see lower condition in this image, right? So another way of looking at off-season imagery can really help inform what's happening during really the season of interest as the crops are growing. This pattern we see here is not so much it's not so much a function of what's happening during the season as it was this last rainfall event, right? So it's a good reminder in this image where these long-term trends that we can understand climatically are important, but these really acute punctuated events can really offset this. If we take an image right after a rainfall event, we could see completely different patterns than if we took it a day before the rainfall event, a week after the rainfall event. So we're sensitive to things that are happening long-term and also temporally. This is a project that we worked on several years ago looking at changing cropping frequency across Zimbabwe. We worked with MODIS and Landsat imagery. The story, of course, in the early 2000s is the disaggregation of very large central pivot plots. So this large central pivot plot gets broken up into these smaller plots, which end up being cropped and harvested at different times. We also have some large plots that were crops twice in 1 year and then transition to single cropping. So double cropping transition to single cropping. So it's very difficult to do just with MODIS, which is this image here, or Landsat alone. Even though Landsat, that bright red is high production, we can see, of course, this disaggregation in both. But in this project, we were interested in cropping frequency, and we knew that MODIS gets a good part of the story, and then Landsat, because of its spatial detail, gets another part of the story. But we wanted to work with them together in the same study. And so being sensitive to changes in cropping patterns, right, and the number of crop types in a given year, which varies here. We just have two examples which aren't good for a Zimbabwe case study, but good graphics for cotton and alfalfa, totally different crop patterns. Being sensitive to the changes in those cropping patterns, we wanted to exploit the fact that MODIS gave us daily images and are really good at measuring this up and down and up and down. With the spatial resolution of Landsat imagery, which takes images every 16 days, but the images are often cloudy, and we aren't quite as good at capturing the ebb and flow as we were with MODIS imagery. We wanted to take the medium scale remote sensing data and really map these changes in intensification and cropping practices so that we could look at a given location and look at it in Landsat and look at it in MODIS. This is the exact same area, but with two different sensors, and basically fuse those two together. And I won't go into the specifics here, but just to say that these systems are compatible. If we know that there is a actual curve, an Ndvi curve of phenology, that's the black line in all these graphs. If we look at Landsat with that, we're going to miss some of those details. But we can put in Sentinel-2, we're going to have more coverage, so that helps us, but we're still missing some of the details. So through a machine learning approach called Kalman Filter, we can apply a model, which I can talk about if you're interested, to basically model these values that are in between our actual observations. Because we know what's happening on the black line with MODIS, but we don't really have a good image of it at the local detail. So we can fuse these and harmonize them. And using data assimilation and machine learning, as I mentioned, we can take these MODIS images and basically dissolve them into Landsat or Sentinel scale resolution to get much higher temporal resolution while maintaining the spatial resolution. So this is a more advanced remote sensing approach, but something you can do in Earth Engine, something you can, that may be of value. So just bringing this example to show that these sensors don't need to stay separate from each other. They really are most powerful when they get brought together. And in this case, we have three different sensors all working together. It's called harmonized, right? Because they're all functioning and basically aiding the other data set. That's all I have. Any questions? Yeah.
Just to the data harmonization assimilation, you mentioned it's doable in Earth Engine. What's the specific approach? What model are you using, and is it limited to Ndvi, or can you also do it in spectral dimension?
Oh, any time series that you have data for, it'll work. So it could be Ndvi, EVI.
But the spectral, like in Sentinel image, you have the spectral channels, which they have a relation, right? So you cannot probably look at them independently, right? If you do this harmonization, while as Ndvi is only one value, right? You have any time series, you can do whatever.
I'm not sure if I followed the question. You can only, this works with only one variable at a time. You could generate multiple variables and compete them against each other, I guess. Yeah, I'm not sure about the.
I guess what I'm asking is, you said you make high resolution Ndvi images, right?
Yeah.
This probably doesn't work for a spectral image, right? You can do it for one channel, maybe.
Why couldn't you do that 3 times then?
Sorry?
Why couldn't you do that 3 times then for all the 3 channels that you want?
Well, I mean, I don't know. That's what I'm asking. Like,
Ndvi is just like any other band. I mean, the way we're treating it in In fact, it would be analyzed just as though it's not generated by the satellite, but we would just be next to NDVI. We could immediately put it in near infrared and just make it run just as well. Maybe I'm not answering.
No, I think so. You're saying you can take a modis RGB and make a higher resolution RGB, which is comparable to Sentinel.
Yeah, it's a little more than that. We're not just taking the MODIS image. So one thing, I guess, an important caveat with this approach is that this completely depends on having a bunch of these images. So if you just had a single MODIS image, you could do a sharpening approach, separate from any of this stuff, which is not machine learning or anything. In Landsat and Sentinel, that would be called pan sharpening, where you take a high resolution pan image and sharpen it. There's a bunch of different ways to do that. But this doesn't quite do that. In effect, what we're rather than taking the MODIS and downs and we're kind of like putting a convolution on it and making it look like Landsat, instead what we're doing is really starting and then taking image from MODIS to help us inform what's happening at that Landsat pixel as it changes. We don't have a observation to connect to dates. So I hadn't really thought about it that way, but that's exactly the difference. Pan sharpening is take an image and improve the spatial resolution with that sensor's own imagery. This approach, we're starting with the high res stuff, and then we're temporally filling in the gaps because we have good, consistent spectral information. They're certainly related. This is just explicitly temporal domain, and it works. It works better in this temporal. It works well in this temporal domain because we know what came after and came before. We can interpolate between, right? If we just had one date, we couldn't do that.
Can you go to the last image? So yeah, it looks like magic, right? So it's like almost like you don't need one. So what exactly are you losing in the process?
Oh, that's a good question. What are we losing? Well, I mean,
Because in pan sharpening, it's very obvious what you're losing, right? Because you can see the original pixels still there. So
Yeah,
vaguely bleeding out of the features, right? But
Yeah.
here you don't. So what?
I don't know if we are losing anything, but one thing we're adding in is uncertainty. When we interpolate these values here, the red synthetic image values, that the spectral values come from MODIS imagery on that day. These we have higher uncertainty, right? Because we're interpolating. It's a little bit simplistic, but we're not just finding 100% we measured it, right? We're estimating, we're interpolating. So in a sense, then these red images are going to have hopefully just as much usability, but there's kind of a caveat to them. And in terms of making it operational, that's a different question altogether. There are a lot of things that need to happen with this approach to make it a real-time, run it, make sure no cloud artifacts snuck through and screwed something up. But cloud masking, you can be really aggressive on cloud masking. You can make everything as clean as possible going into it, so you would expect less of that. I hadn't thought about what you lose. I don't show it here, but when we do this space state model, when we apply it, areas or image dates when you have a long run since the last Landsat or Sentinel observation, or one that goes until the next valid, your uncertainty just propagates. It's really high, and then it actually is going to peak at that date that you use, and then it goes down again. So it's sort of there's an uncertainty band that would go with this.
It peaks at the first image after the gap.
Well, what you want to, so there's a balance, right? If you have a gap between the green and the blue, so here we don't need a synthetic image because that's like maybe they're the next week, so there's no value to add in another one there because it's good enough as it is. But let's say we go, here's a good example, the green to the blue, that's a long period when we don't have any imagery. And so every time we get away from this, we have less confidence about the actual value. So the choice, this is just kind of a graphic for illustration purposes, but the choice really where we would want to put that, if we put it here in this graphic because this is at the end of the curve, so it establishes the baseline. But to be honest, this makes this a little bit redundant, perhaps. under normal circumstances, we would put this right in the middle of the dates, right? You just want something to fill the gap. And so all things being equal, you choose the middle one, but that happens to be the farthest from both, and so your uncertainty is the highest. If that makes sense.
Are we using like some sort of like harmonic model to fit it here and addressing the anomalies if there are like changes in weather or like something happens?
Yeah, no, that's a good question. There's no, on the second board, there's not really an assessment. The MODIS NDVI is what it is, and so contextualizing, interpreting it, that's where we bring in, well, this was a drought, or this was a, intense rain event or something. But the fact that there's a climatic deviation doesn't affect the value of this, just the input data are as they are. The use of it might be limited then, right, if it's an anomalous event, but it shouldn't throw off the algorithm. Similarly, missing data, this whole thing is designed to work with missing data, to address missing data, so it works really well with our data gaps. What was your first question? Sorry.
Is it like the model, is it kind of a harmonic model that we are fitting here?
It's not, there is a assumption of seasonality and phenology built into it. It doesn't explicitly do a harmonic fitting. There's no Fourier transform, there's no decomposition to seasonal curves or anything like that. There are models, Star FM uses that approach. This is a different approach. It's called the Kalman Filter. Kalman Filter was originally created by NASA scientists when a satellite went behind the Earth, for example, or behind the Moon, and you wanted to still have a good estimation of where the satellite was at a given location. You know where it left, you know where it is, and you have the physics of where it should be. But you want to also be able to sort of predict, given all these uncertainties and eccentricities, where it might be. So that's where this came from, trying to understand orbital mechanics, or trying to estimate orbital mechanics. So in that sense, it worked in that sense because you have a mathematical orbit, and here we have this mathematically defined typical phenology, which informs the model. It's built into the estimation of the curve, but there's not an explicit harmonic decomposition that's happening. The historical curve is what it is, and the curve that we're empirically measuring just by MODIS, we get a new MODIS image and we put this into the curve and then update the model. There's no need to do a harmonic fit necessarily. That could improve it, actually, if you kind of try to constrain it more, but the way it's run so far, we haven't. Go.
With this advancement in this technology, I'm wondering either we can use this tool to look at other food security dimension other than the production, like access, utilization, or stability.
Oh, good question. I suppose, I mean, this is really still at a level of condition, for better or worse, right? This just tells you NDVI. But then if you put that into a framework where you're interested in other sort of derived variables, where a change in NDVI by some amount over a time period, it could perspective. It would find a good warning of a cropland abandonment, or annual deviation. This is always cropped. This year there's no cropping happening. That would be a deviation, but at an annual level, not so much a seasonal. But at the end of the day, this is just more condition estimates. So if you have a sort of temporal understanding of how things should look, and if you know what a deviation looks like, then this will aid in that. If anything, this would give you a heads up on that change, because you don't have to wait to the next image.
But there's no some case studies in the where we are just looking into these dimensions or using this motion tool.
I'm not sure.
This in particular we haven't implemented yet, but it's something that we can try to do. It's an opportunity.
Yeah.
Is it possible for you to make this presentation available?
Yeah.
Yeah, that'd be great. That'd be really useful.
Any other questions? All right, thanks, everyone.